And so let's look at the vibrational combination bands and overtones. This will expand the symmetry operations, the use of the character table, to include multiple vibrations being excited at the same time. Now this is hard to understand conceptually. A single photon of light comes into a molecule and excites multiple vibrations. So I don't exactly know physically how that happens, but you know, multiple bends and stretches gets excited by a single photon of light. And so there's something about the resonance of those wave functions and light that all combine so that you get excitation. Now, it does have to obey the symmetry rules, and so we'll at least look at the symmetry to see if it's allowed for that combination to happen. And so we have these CO2 stretches that we've talked about already. One of them is infrared active, one of them is Raman active. Can you tell from the pictures, just looking at those vibrations, which one is IR active? Okay. Remember that infrared absorption is direct absorption of light, and it's an oscillating dipole. Light is an oscillating dipole. And so it has to interact with an oscillating dipole if it's just going to be directly absorbed. Okay? So look at that top picture. The carbon is slightly more positive than the oxygens. And so when that carbon moves to one side of the molecule, there's a little bit of a positive end of the molecule and a bit of a negative end on the other side. And so as that carbon is oscillating between the two oxygens, there's a changing dipole. So the top one is asymmetric and it has an oscillating dipole. It can absorb light directly. It's infrared active. You can also look at that if we were to draw the arrows. So here's the molecule. The z-axis is the axis of the molecule. I look at my arrows and I see that the carbon is moving over here, the oxygens are moving that way. Essentially all of the motion is in the z direction or negative z direction, and it's going to oscillate in the z direction. So if I go to the character table, the infinity h, I'll see that z is on is on a row that's has a symmetry. Gosh, I don't remember what it is. Well, that's up here. Yeah, it's A1U. And so that is the description of this motion. That's also the description of light that could excite it. So in vibrational spectroscopy, this one is always the top row. We messed that up on the last test thinking that in visible spectroscopy or MO theory, where you're looking at electronic energy levels, that this one was always the top row. But no, in vibrational spectroscopy and rotational spectroscopy, this is the top row. This one is the symmetry of the motion, and then this is light. And so we can see that light is going to be compatible with the symmetry of that motion. The U's are going to cancel and make G's. A1s times A1s are A1s. So this is definitely going to be allowed. So if you could just look at that and say, okay, from the motion of the vibrating molecule, I would get these arrows. Now, I can't give you an animated picture on the test, but I can give you the arrows. But I would like for you to at least mentally see these arrows and be thinking of that picture. Okay, so the carbon's moving to the right, the oxygens are kind of moving to the left, and sometime later the arrows switch directions. And so this picture is trying to represent what you see on the top. Okay, now let's look at the other one. These are the arrows that I would draw for the bottom one. So the oxygens are stretching out symmetrically or coming back in symmetrically. That's going to be z squared. If I were to look at that, stand on the origin, look this way, I see the arrow going away from me. I look that way, I see the arrow going away from me. So it's the same in positive and negative z, so that would be z squared. And I look on the character table, find z squared, it's going to be a1g. It's going to be on the top row. So for this one, we have a1g, a1g, a1g. This one's a1g because in vibrational spectroscopy, the ones on the right are always a1g. This one is the symmetry of the motion. And this one is z squared. The Raman experiment, z squared. And so I'm coming in with 2 photons of light that can excite this motion, and this is going to be allowed. So this is the Raman symmetry analysis of this particular motion. Now let's show why this particular motion is not excitable by infrared light. If I just did z and not z squared, I would have a1g for the motion, a1g because the ground state is fully symmetric. But if I put a1u here, then I've got g times u is u, and then u times g is g times u is u again, and so the end result is going to be u. It's going to be a1u, and that's not top row, so that's not going to be allowed. And so this integral will equal 0. This one will not equal 0. So this one is allowed. This one down here is not allowed. So let's practice this same kind of thing, but with the combination bands and overtones. So we have these would be direct absorption or the Raman scattering, but we have in the spectrum for CO2 these other peaks that show up further up in the spectrum. So we have direct absorption, we have the Raman, those are the regular peaks that we've dealt with, but then we have this very strange rotational vibrational activity up at 3,684 wave numbers. And I said, what is that? It seems to be related to CO2 because when we clean the CO2 out of the spectrometer, those peaks go away. When CO2 is strong, those peaks appear. So we know those peaks are related to CO2. We analyze what kind of vibrational frequencies would get us up there, and we realized that if I took one of the new 3 vibrations and 2 of the new 2 vibrations, I would get to 3,684. And so I'm going from 0, 0, 0, the ground state for all 3 vibrations, and I'm going up to 1 excitation in new 3 and 2 excitations in new 2. That gets me this frequency right here. Because I'm adding 700 wave numbers twice, so that's 1,400 wave numbers added to whatever the previous one. Let me go back and find it. Actually, I think I have it next. Just a second. Yeah, so I have 2 times the 700 wave number frequency plus 2,300 for new 3 gives me 3,700. So that gets me really close to that 3,684. So that's how you would determine what a combination band is. You would figure out what combinations of the fundamental transitions can be added together to get this new peak that I find. And so that at least tells us that that's a possibility, that I could have 2 new 2s plus a new 3 added together to get me to the 3,684. But is the symmetry work out? What if you had 2 or 3 ways to get there? You would want to see if all 3 ways were allowed or if only one of those 3 ways was allowed. If you figured out that only one of the paths to get there was allowed, then you would have assigned it. You would know exactly. That's the way that light excites this molecule. Yes?
Where did the 2,300 come from?
That is this distance right here. So this one right here, this distance to there is 2,300. Yeah.
Oh, I didn't see that.
Yeah, I didn't see it either earlier when I was looking for it. So this is 2,300. It's a Raman active mode, so it does not show up in the infrared. But when you add in 2 of these, you get up to this level, and it is infrared active. We'll see from looking at the symmetry. So look at this. We have 3 ground states, so we have 3 A1Gs here. we have light, which is A1U. We have one of these, which is A1U here. So that's this one. And then we have two of these E1Us, go right there. And then we have nothing happening to nu 1. So nu 1 is still 0, so we have that. So that's as complicated as it gets in the whole course. Okay, that's the longest one that we'll do, where we have, 3 vibrational modes changing to 3 different vibrational modes. One of them stays the same, but yes.
We're not adding any of the A1G to marketing again.
We're not doing what?
I don't know. It says 0 to 1. So like I understand 1 is we have one A1U.
Yes.
2 E1U.
Yes.
But there's 0, so why do we have the A1G?
Because that's the symmetry of that ground state. So it's staying in the ground state. And so I'm just taking all of the symmetries of all of the wave functions. Remember, these quantum numbers are telling you the wave functions that are all interacting with each other. Okay? And the A1G to A1G is really not affecting anything, but I'm just putting them in there to show you that that wave function is still there. So the molecule that's in the ground state has a symmetric wave function. And so what we're writing in this integral, and remember this is Dirac notation, so this is an integral, and we have 3 vibrational modes. So we have 3 wave functions multiplied by each other, and that's interacting with light, so another function is multiplied by those. And then we have the wave function for nu 3 that's excited into the first excited state, and nu 2 is excited to the second excited state. And so we're taking into account 2 jumps of that wave function, and then nu 1 is not excited at all, it's staying in the ground state. So we have the symmetries of all of those wave functions multiplied by each other. So I can't imagine how complicated it would be to actually see the wave functions all multiplied by each other, but we can look at the symmetries. And so even though this looks complicated, it is infinitely less complicated than actually showing the math behind those things. And if the symmetries work out, then the math, we know if we were to integrate that, it would be non-zero. Did that answer your question?
Yeah. Yeah, it did.
Well, what's the question about the A1G? You said something about adding them. Yeah.
Well, like what would be the difference if you had one of the ground state? If you had, if the ground state you had
The ground state.
like instead of 0 it'd be 1.
Oh, but see, the ground state can't be 1. So that would be the first excited state. Okay? And so if it's a quantum number of 0, that's the ground state. So we have 3 ground state. The molecule starts in the ground state vibrationally. And it's going up to this level here. And this is the energy level. This may be something that will help. That's the energy level for the whole molecule. Okay, so that whole molecule is excited. And if you ask it, how are you excited? It says, I don't know, let me see. Oh, I've got my first vibrational frequency is excited by 1 quantum, and my second vibrational frequency is excited by 2 quanta, and my third vibrational frequency is in the ground state. So just that third vibrational frequency is still in the ground state, but the first 2 vibrational motions are excited, and that's the energy level for the whole molecule.
Okay.
Yeah, and so then we have all 3 of those wave functions have certain quantum numbers, and those 3 wave functions are multiplied by each other. And that's the symmetry of this thing on the left, right here. So that's the symmetry of this level there. And this is the symmetry of this level down here. And so we're connecting this symmetry to that symmetry with light. So it's the same kind of concept, the symmetry of the ground state, the symmetry of the excited state, and whatever that excited state has. And in this case, now that we've got multiple vibrations, it's got multiple things that can change the symmetry. Like I said, this is the most complicated piece really in the course in terms of being able to understand how the quantum numbers figure in. And then on top of this, you can have the rotational changes like the P, Q, and R branches. Yes?
So will we be given the symmetries of the vibrational modes?
Yeah, so you would have to know this down, well, you know this one, the ground state's top row, okay? But you would have to know this one, right? So that's the symmetry of vibration 3, and that's the symmetry of vibration 1, or vice, do I have it backwards? No, this one's 3 and that one's 1. And then this would be the symmetry of vibration 2. Okay, so you would have to know those vibrational assignments. And you might get them from the pictures, the arrow diagrams. Okay, so if this one is, let's see which one is this. So this one is nu 3, and this one is nu 1. You should be able to assign the symmetries. And so let's walk through this long combination band. So that's our Dirac notation for this absorption. And a lot of these are simple. We have A1Gs times A1Gs. All of those can be reduced to A1G because it's all top row times top row. Then we have this product here, the A1G times A1U. That gives you A1U. Then the next two, the U's cancel out, giving back to A1G. Then A1G times E1U. Again, anything times top row is returned. So E1U times top row is E1U. And then we have something interesting. We have a two-dimensional irreducible representation. You use the Millikan notation. We have a two-dimensional one times a two-dimension. So the result should be 4 dimensions, meaning we should have a couple of single dimension, the A's, and one E. So we have an A1G, an A2G, and an E1G. So we get that from the direct product tables, and we can look those up. And then we have A1G times all of those. And so that's going to give us this full set. So there would be the integral of 3 functions that are added together, and one of those functions is going to have a non-zero integral, the one that's A1G. So that's why we say if the result contains A1G or contains the top row, then it will be non-zero. And that will be allowed. Okay, sorry. So that's that combination band for 0, 2, 1. And so then we get to the spectrum, and that's this one right here, 3684. So that's still CO2. It just happens to be a combination band. You could do the same kind of analysis for the 1 plus 3 combination, this 3730 here. And then this says water down here. That's meant to just point to this little fuzz that's on the spectrum there. Okay. So water is just that little bit down on the left. Those other 2 peaks are associated with CO2. Now here's the ones for acetonitrile. We didn't analyze these, but we certainly can. So in this acetonitrile spectrum, we had some combination bands. Nu 3 plus Nu 4, and Nu 7 plus Nu 8. And it's given the symmetries of those. So we can kind of verify if those symmetries work out. And then we also had an overtone, 2 Nu 8. So the Nu 3 plus Nu 4 combination band, you see in Dirac notation we have zeros on the right, which is the ground state, and they're going to 1 quantum excitation in Nu 3, 1 in Nu 4. Now this is acetonitrile. We have 6 atoms, so n equals 6. So 3 times that is 18. Minus 6 would be back down to 12. So we have 12 vibrations. We're only showing you the 2 that are changing. So we would have 12 zeros on the right, and we would have 10 zeros on the left with 2 changes. The Nu 3 and the Nu 4 would be 1s. And so I've simplified it and gotten rid of all of the ones that don't change and just showing you the ones that change. So these are the symmetries for all of those. This is pretty easy if you look at it. That's top row and it's all the way across. So we're using Z-light, and you can just clean this all the way up and get down to A1 being the integral of an even function is going to be not equal to 0. So this is an allowed combination band. We can do the Nu 7 plus Nu 8. It's a little more interesting. So we're exciting in the 7th vibrational mode and the 8th vibrational mode, and both of those are E. So simplifying the first few, we get down to A1, and then we have E times E. So we go to the direct product table. We see that E times E is A1 plus A2 plus E. And because it has top row inside, then it's going to be not equal to 0. And so this would be an allowed combination band. Now there are plenty of combination bands that are allowed that you don't see in the spectrum, but the integrals are so small that you just don't have much intensity. For whatever reason, these combination bands have a strong enough intensity that we can see it in the infrared spectrum. So, yes.
You have to check with X and Y files like too.
Oh yeah, let's do that. I think that's the next one. So that was with Z. So here's X, Y. So great. It's almost like a plant. And so then simplifying, we have E. Now we're going to have 3 E's. So this is going to get pretty complicated. So we have E times E is A1 plus A2 plus E. And now we just multiply through. So we have E times A1, E times A2, and E times E. So that gives us an A1, an A2, and 3 E's. So because the E times A1 was E, E times A2 was E, and then you had E times E was where the A1 and the A2 came from. And then that third E.